In the previous video, I've been talking a lot about how to deal with circuits that has more than just one circuit element. In this case, it's a resistor and a capacitor in one AC circuit. So we have dealt with something that involved Pythagoras theorem, and we have dealt with something that involved inverse tangent. So I never really specify any new formula in this thing, but actually I derived something new over here, and I apply Pythagoras to do something here. So there's actually formula that is catered to this kind of situation, but I'm just showing you that it can be done just by knowing Pythagoras theorem and inverse tangent. So now let's move on to talk a bit more about the actual equation that you can use to solve this kind of problem. And to talk about the equation, we move on to another kind of circuit, which is called an RCL circuit. So this RCL circuit, RCL stands for resistor, capacitor, and inductor. So essentially, you have a RCL series circuit, which you connect a resistor, a capacitor, and an inductor through a series AC circuit. So if now you have three circuit elements, then your phasor diagram will be the overlap of the three phasor diagram of the three circuit elements. So you have the purple arrow and the green arrow that represents the phasor diagram for pure resistor, and you have the purple arrow and the red arrow to represents the phasor diagram for the capacitor, and you have the purple arrow and the blue arrow to represent the phasor diagram for the inductor. So if you have three circuit elements being connected into one series circuit, what you do is you merge the three phasor diagram together, so you give you this blue, red, purple, and green phasor diagram. The yellow is still not included yet. So these four arrows here form the phasor diagram for this RCL series circuit. But the purpose of we doing phasor diagram is to know how all the things that are in phase and not in phase, how do they interact with each other. So in this case, we have one voltage here, which is in phase with the current, but we have another 2 voltage that is oscillating not in phase with the current. So we want to see how these 3 voltage actually interact with each other to give out the overall voltage. So the overall voltage, you can think of it as the voltage that is being supplied across this AC power supply. You can think of it as the overall voltage across this whole three circuit elements here. So the overall voltage, based on the phasor diagram, is just a vector sum of the 3 voltage here. So you're basically adding up the vector of the blue vector, the red vector, and the green vector together, and that will give you the resultant vector, and that resultant vector is the peak voltage of the overall AC circuit. Okay, so in this case, I draw my peak voltage for the overall circuit over here, which is at the 4th quadrant. So if that's the case, I think you can know that the x-axis is the x component of this yellow arrow here is fully contributed by the voltage of the resistance. Whereas the vertical component, in this case going downwards, the vertical component of this yellow arrow here is contributed by this blue phasor and the red phasor over here. So in this case, actually we can make slightly more deduction and say that for this case, the peak voltage for the capacitor is actually larger than the peak voltage for the inductor. So for this case, you have a longer red arrow compared to the blue arrow. So if you add up these two vectors which are in opposite direction, you end up with a vector that is pointing downwards. Adding this vector pointing downwards together with a vector that is pointing rightwards, and there you get this overall this resultant vector which is pointing in the 4th quadrant. Okay, so basically it's just showing you how do you add up all these voltage phasors together. Okay, so the way we find the magnitude of this resultant vector here, to find the magnitude of this peak voltage of the overall circuit, what we do is we first find what is the resultant in the vertical component. Okay, the y component, what is the resultant voltage, peak voltage actually. Okay, so if what can we do is we take the up minus the down, Then if it's a positive answer, then it will be pointing up. If it's a negative answer, then it will be pointing down. Again, you take the voltage of the inductor, the peak voltage of the inductor, minus the peak voltage of the capacitor. If the up minus the down is positive, then it will be an arrow pointing upwards. If it's a up minus down and you get a negative, it means the down is longer, so your resultant vertical component is pointing downwards. Okay, so that is represented by this part over here. You are finding the y component of the peak voltage by getting the pointing upwards minus the pointing downwards. Okay, so this value here represents the y component. And of course, if you're doing a Pythagoras theorem, you need to do it with an x component. And for this, from this phasor diagram, I believe you can see clearly that the only component in the x direction will be the one contributed by the resistor. That's why the peak voltage of a resistor square plus the y component of the peak voltage square, which the y component is contributed by the inductor and the capacitance. So from here, we can also know that basically all the peak voltage here has a component of peak current in it. So you can break down the peak voltage for resistor into I naught R. You can break down V naught L into I naught XL, the inductive capacitance. Then you can break down V naught C into I naught XC. And through factorizing out the I, you can get I naught, then you are left with also a Pythagoras theorem, but inside it's R square, the resistance square, plus the inductive capacitance minus the capacitive reactance square. So this is like the y component of the opposition effect, the y component of the impedance. This is like the x component of the impedance. Impedance itself is a scalar value actually, but this thing is just to show it on the phasor diagram. It can be represented as the y component and the x component, but the value itself is actually just a magnitude only. Okay, there's no direction. The direction here is just to tell you the direction of the voltage. Okay, the overall voltage, this is the direction. How much is it phase different from the current? Okay, the z here does not carry any direction actually. The z here is just a value, and the value can be obtained through this formula because you know that V naught are all related to I naught in this sense. Okay, so this z here is what we call the impedance, and therefore impedance is just a ratio of V naught across the circuit to I naught flowing in the circuit. So V naught is over here, what you measure over here. I naught is what you measure along the circuit. So you take V naught divided by I naught, and there you get impedance. Okay, so if we are talking about impedance, we can redraw the phasor diagram using this way. Okay, again, this is not an actual phasor diagram like what we discussed in the previous question, because R here, inductive reactance here, capacitive reactance here are not rotating vectors. They do not change with time. Okay, they are constant values. These are only showing you how should you do a sum to obtain the impedance. Okay, this is just showing you how to do the sum to obtain the impedance. In this case, you take the up minus the down, get a y component, then you find the x component, which is resistance, and you do a Pythagoras to find the resultant length, okay, which is the impedance. So this is the magnitude of the this is impedance, and for this phasor diagram, these steps here allow us to find the magnitude of the peak voltage. And next, we can find the phase difference between the current and the peak voltage. The peak current and the peak voltage, what is the phase difference? What is the phase angle between them? To find this angle, we again relate back to our calculation involving vectors. It's basically just inverse tangent of the y component divided by the x component. So tangent phi will be the sum of the v in the y direction divided by the sum of v in the x direction. But again, we keep it the same convention. You take up minus down. That's why it will be V naught in the V naught for inductor minus V naught for capacitor. So that will form the y component's peak voltage, and V naught R will form the x component. Okay, we are talking about phasor here, but I keep on talking of it as like vectors, but they are not actually vectors. They are rotating vectors, and the rotating vectors is just to show you the phase relationship. but the process of doing the calculation is similar like handling it like vectors. Okay, but these values here are actually scalar values. I know it's a bit confusing, but you just need to know that it operates like a vectors, but it's not exactly a vector. The vector there is just to show you the phase relationship. Okay, so once you have reached this stage, again, you can settle down here. This is also one equation for you to determine the phi by doing an inverse tangent, shifting the tangent over here. But you can also proceed further and extract out the peak current from all these three terms over here. So if you extract out the peak current and you cut it off, then you are left with the inductive reactance minus the capacitive reactance, which is the y component of the impedance, divided by r, which is the x component of the impedance, and do an inverse tangent. Okay, so these are ways for you to determine the phase angle, and if the phase angle is positive, it means V naught is leading I naught, the overall V, the V for the AC circuit, is leading the I naught flowing through the circuit. If it's negative, then the V naught across the circuit is lagging behind the I naught by phi. Okay, so I'm just giving you the actual formula that is being discussed in textbooks, but if you see, it's just basically Pythagoras theorem and tangent phi. Okay, so let's try that again, use what we have learned here in a more formal way. We learned this a formal way, and let's try and apply it in another question.